a cube of the unit size. So that means each H has the length of 1. Many times when, for people, if in the future, if you have the chance or if you want to go for the further studies, if you have a chance to go to the solid mechanics viewpoint, many times we choose I say this is a material model. So basically for everyone to choose a material model which is best for the use of that specific studies. So don't try to complicate ourselves by picking up an inappropriate or too complicated model. The material model is to use to simplify the problems in a good sense. So here let me try to use the one-on-one. And for this material model, for example, here is XYZ directions. And like we did before. And imagine this cubic material is immersed in the deep of the water. So that means this will experience from the 3 directions the pressure. Okay, P is the uniform pressure. So this is one example I try to describe for this exercise. So P is not a force, and if you wish, I can make more kind of the arrow. So basically to indicate the P is the uniform pressure applied to everywhere on the surfaces of this cube. So for this case, we might use Hooke's law to study whatever the response of this material to such loading. So from Hooke's law, we have sigma epsilon x equal to this one minus mu y plus z, and y equal to So that is Hooke's law. And we simply, again, the first step here, we try to adopt the boundary conditions. And for these boundary conditions, the stress, the loading, the stress is from the pressure. The pressure is compressive. This compressive pressure loading is uniform everywhere. So this would be equal to minus P. This will be equal to minus P. Okay, we simply plug in all the numbers, etc. Okay, etc. So from this case, we can calculate the strength. Let me write here. This one will be equal to minus P E 1 minus 2 plus 2 nu. Very straightforward substitutions. Imagine that be yourself. You do the scuba dive into the water, and then on a certain distance, you will feel your body shape is changed. Actually, your volume of your body changed due to the pressure. Your body squeezed a little bit uniformly. Right? So in this way, for this case, we want to know, for example, what is the volume change of this material. the volume change is the volume after minus the volume at the original. So here the initial volume equal to 1. The after loading volume will be equal to, after loading, you can imagine the whole situation become like this. In the x directions, y direction, and z direction, we already have the strain in each direction. So in each side, for example, this is the dimension in the x direction, and that is original length plus the strain multiplied with original length. This is the deformation. So 1 plus deformation equal to the final length in x direction. The same thing in the y direction. This is 1 plus strain multiplied with original length, so that is equal to 1. So this represent is the final length, the final dimension in y direction. In the z direction, the same thing is epsilon z. So the volume after loading basically is the 3 dimensions multiplied together, 1 epsilon x multiply 1 epsilon y plus multiply 1 epsilon z. And this one can be writing as 1 plus epsilon x plus epsilon y plus epsilon z, and plus the higher order terms. Higher order terms is nonlinear. For example, epsilon x, epsilon y plus something something plus epsilon x, epsilon y, epsilon z, and there's other a few terms. So those one we call it called the higher order terms. Because most of the time the epsilon x, y, or z by themselves are very small. So basically multiplication of the small numbers is even smaller. So basically for higher order terms we can approximate equal to 0. Okay, this approximation should be good. So that means here the volume change delta V respect to the ratio, the original volume, the initial volume. Initial volume equal to 1. We want to take the similarity of the strain. Remember, our strain is deformation divided by initial length. Volume change is the deformation in volume divided by initial volume. So the same concept of the strain. But somehow here we take is about the volume change. So this one we do the calculation. Basically, delta V equal to this amount minus this one. So delta V equal to 1 plus epsilon x plus epsilon y plus epsilon z minus 1 and divided by 1. And so therefore the ratio of the volume change basically is equal to the 3 numbers plus together. This volume change, sometimes we give the name dilatation. Dilatation. Something like this. Dilatation, that means the change in volume, and sometimes expanding, sometimes it's shrinking, depends on the loading condition. But that ratio is defined by this. So usually we use this notation is we use E. Okay, we use the ABCDE, the lowercase e, as a symbol for this. So therefore, from here, let me summarize. So therefore, E will be equal to the 3 terms, epsilon x plus epsilon y plus epsilon z. So simply we plug in the 3 informations. Basically, that is becoming is minus p times 3, 1 plus 2 nu divided by E. This number. Okay, this is an example, it's not a formula. But using this example, I'm going to introduce additional term, and which is we call the derived term. It's called the Bach modulus. Bach modulus is a material constant, material properties, and we use K, and that is a very common symbol for this. This is to describe the ratio of this example, and K by definition is, do you remember, compared to our Young's modulus, is the loading divided by strength, right? So loading divided by strength. So this one, in a similar fashion, this is the loading. Loading is minus P. Divided by corresponding the strength. This is for one-dimensional, and this is strength-like quantity for this case, which should be the whole things. So that is E. Okay, so numerator here I make up is one-to-one comparison. On the numerator, that is the force or loading line, loading equivalent quantity. In the denominator, that is strength equivalent quantity. Okay, Bach modulus simply is to describe the ratio between the pressure and the volume change percentage. Okay, and so likely depends on the every single person's the body density. So likely everyone's Bach modulus will be different from another's. Depends on if you go scuba dive into the water, you can try if you can know the change in the volume of your body. Okay, now for this case, you can see we plug in all the things here. Basically, that is equal to E3 1 plus 2 nu. So as long as we know the Young's modulus, we know the Poisson ratio. K is a derived quantity. And these material properties is not often used compared to E or nu, but our textbook have this kind of introductions, so I kind of give you the head here. The next one, any questions? Yes?
So will it always be negative P, or is it just specifically for this case because negative P is the uniform pressure?
Yes, and usually the definition of the Bach modulus is from pressure here. But that concept can be applied to, say, tension. Basically, the K is the ratio. I think the easiest way is this. K is the ratio between the magnitude of the pressure
magnitude of the pressure
yes,
to the
yeah. So always K is the magnitude. Always we plug in the numbers. All K we simply take is a positive. If plug in the definition is right, that should be positive. But
if it's not positive, do we take the absolute value?
You just take the absolute value.
Yeah.
But if that is not positive, then that means your substitution has some kind of the inconsistency.
Okay.
But that doesn't matter which for. So anytime when you consider a change in volume, and then likely right away you have to pick up the Bach modulus for that kind of situations. Dilatation, volume change, that is the same thing, and Bach modulus, they are always come together. The last one, and right now how many material properties we have? So far we have the material properties. We have introduced is Young's modulus, Poisson ratio, Bach modulus. And again, as long as we know any two of them, then the others are derived. The final one I want to give to you is this one, G. G is called the rigidity modulus. This is the last one I want to introduce to you. in this chapter. Actually, that is the last one in our class in ES 331. And what is G? And this one basically is relate the shear stress, shearing stress. To the shearing strength. And compared to this one, this is Young's modulus. This is about the normal stress and related to the normal strain. Okay, so that is the little bit different, and rigidity modulus is for shearing, compared to E, that is for normal. And before we define the G, which is very straightforward, I need to define what is a shearing strain. And shearing strain, again, that is the strain is always a quantity to measure the deformation of the shape or the geometry. The normal strain is about the deformation, elongation, or shrinkage. Shearing strain is different. That is about the measure of the angles. For example, consider a 2D material model. And again, I pick this material model is for demonstrations. We always, keeping that in mind, we always pick the model that is appropriate for the specific purpose. So if we consider a 2D model, and for example, that is a unit in the dimensions, and that one, let me define the XY dimensions. So if for this unit model that is under the shearing stress or the shearing force like this, so basically this shearing, let me call this tau, okay? And in static equilibrium, the magnitude of the four quantities of four shearing stress must be equal in magnitude. And this shearing, in response, will try to not to stretch, try to change the shape from the square to a rhombus, and that rhombus can be described in this way. So I schematic draw it. Okay, not so perfect, but just show you. Okay, so this is the deformed shape. And for the shearing, applications of the shearing stress is the first one, it won't change the total volume. So that means the area of the rhombus will be equal to the original, the square, which is equal to 1. Okay. The second one, it will change is this. It will cause a change in shape, and the shape for this particular model is from square to rhombus. How do we quantify such a change? We use angle. What angle will be appropriate? We use, for example, we can use this one. And here, if our application is uniform applying to the perfectly square, then the two angles should be equal. Okay, and so that means we can try to measure the change of the angles here. So we can use either this or this to represent how large the shape of the change. And this one sometimes for convenience, and this will be equivalent to this case, x and y. This is our original 1 and 1. And for illustration, sometimes the model can be simply equivalent to this. So simply is this, you try to imagine if we do a little bit rigid body rotation of this rhombus such that this side align to this side and become like this. So that means this angle is the summation of this one plus this one. And we define this is gamma, this angle is gamma. And in particular, gamma in the xy plane. So I use gamma xy. So here we cause the change in the shape, and we use gamma xy, which is the angle, to measure the change. And this is sorry, this is too low. I keep that in mind. So the last line is we use gamma xy, which is an angle, to measure the change. And here the gamma xy is we call the shear strain. Gamma xy is called the shearing strain. So now how to define the shear strain? Simply that is the change of the one side from his original side, and that is defined by angle. So depends on which standard you want to adopt. If you like to adopt this one, then either each side of the change, that is half of the shear strain. Or if you adopt this model, then the shear strain simply measure is the change on the one side. The other one we fix. Okay. Any questions? So if we change our viewpoint, for example, this would be the one side of the cube. If we change our viewpoint into xz plane or the yz plane, then we have the angles in the other in the other two directions.